Voltage codes are essential for identifying wires within industrial electrical panels. For a 24-volt alternating current system, the phase or hot wire is typically blue, the neutral wire is white, and the ground wire is green or green with a yellow stripe. Moving to a 48-volt alternating current system, phase 1 or hot 1 is brown, phase 2 or hot 2 is black, the neutral is white, and the ground is green or green with a yellow stripe. In a 120-volt alternating current system, the phase or hot wire is red, the neutral wire is white, and the ground wire is green or green with a yellow stripe. For 240-volt alternating current systems, phase 1 or hot 1 is black, phase 2 or hot 2 is red, the neutral is white, and the ground is green or green with a yellow stripe. For higher voltage systems such as 480 volts alternating current, phase 1 or hot 1 is brown, phase 2 or hot 2 is red, phase 3 or hot 3 is orange, the neutral wire is grey, and the ground wire is green or green with a yellow stripe. Finally, for 600-volt alternating current systems, phase 1 or hot 1 is blue, phase 2 or hot 2 is orange, phase 3 or hot 3 is yellow, the neutral wire is grey, and the ground wire is green or green with a yellow stripe. In addition to voltage-specific color codes, there are general color guidelines for conductors. Black usually indicates a phase or hot conductor. Red can also indicate a phase or hot conductor, especially in 480-volt systems. Blue is typically used for neutral conductors, but this is inconsistent with some voltage standards. White is also used for neutral conductors. Green or green with a yellow stripe always indicates a ground conductor. The insulation color of a wire also provides information. Black insulation is often ultraviolet resistant and suitable for outdoor use. Red insulation is heat resistant and suitable for high temperature applications. White insulation is general purpose. Blue insulation is cold resistant and suitable for low temperature applications. Green insulation indicates a bit-round conductor. It is important to note that these color codes are generally accepted in North America and adhere to some international standards. However, always consult local regulations and industry best practices for specific applications. Using the correct color codes ensures safety and proper identification when working with electrical systems. Electrical wiring and cabling is the backbone of any industrial facility, and understanding the color codes associated with different voltage levels and functions is paramount for safety and efficient maintenance. These color conventions provide a standardized way to quickly identify the purpose of each wire, which is critical for troubleshooting repairs and new installations. Firstly, consider the voltage levels. The most common alternating current voltage levels found in industrial settings are 24 volts, 48 volts, 120 volts, 240 volts, 480 volts, and 600 volts. Each voltage level has a specific color code associated with its phase conductors, neutral conductors, and ground conductors. These standard color codes are essential for safety and efficiency. Secondly, the 24-volt alternating current systems commonly used for control circuits and low voltage applications typically use a blue wire for the phase or hot conductor. The neutral conductor is usually white, and the ground conductor is green or green with a yellow stripe. This color combination helps technicians easily identify the low voltage control circuits and differentiate them from higher voltage power circuits. Thirdly, the 48-volt alternating current systems, also used in control circuits, employ a slightly different color scheme. The first phase or hot conductor is brown, while the second phase or hot conductor is black. The neutral conductor remains white, and the ground conductor is green or green with a yellow stripe. The use of brown and black for the phase conductors distinguishes this voltage level from the 24-volt system. Fourthly, the 120-volt alternating current systems are commonly used for lighting and small power tools. The phase or hot conductor is typically red, while the neutral conductor is white, and the ground conductor is green or green with a yellow stripe. This color code is widely recognized and used in both residential and industrial settings. Fifthly, the 240-volt alternating current systems are used for larger appliances and equipment. The first phase or hot conductor is black, and the second phase or hot conductor is red. The neutral conductor is white, and the ground conductor is green or green with a yellow stripe. This color combination helps differentiate the 240-volt circuits from the 120-volt circuits. Sixthly, the 480-volt alternating current systems are used for heavy machinery and large industrial equipment. The first phase or hot conductor is brown, the second phase or hot conductor is red, and the third phase or hot conductor is orange. The neutral conductor is gray, and the ground conductor is green or green with a yellow stripe. The use of 3 different colors for the phase conductors is essential for identifying each phase in a 3-phase system. Seventhly, the 600-volt alternating current systems are typically found in very large industrial facilities. The first phase or hot conductor is blue, the second phase or hot conductor is orange, and the third phase or hot conductor is yellow. The neutral conductor is gray, and the ground conductor is green or green with a yellow stripe. This color code is distinct and easily identifiable in high-voltage environments. Furthermore, in addition to the voltage-specific color codes, there are general guidelines for conductor identification. Black wires generally indicate a phase or hot conductor. Red wires can also indicate a phase or hot conductor, especially in 480-volt systems where they are used for one of the phases. Blue wires are typically used for neutral conductors, although this can be confusing because blue is also used as a hot wire color in some voltage systems. White wires are also commonly used for neutral conductors, providing a consistent color for the neutral connection across different voltage levels. Green or green with a yellow stripe wires always indicate a ground conductor, providing the universal color code for grounding purposes. The insulation color of electrical wires provides additional information about their intended use and environmental suitability. Black insulation is often ultraviolet resistant, making it suitable for outdoor applications where the wires are exposed to sunlight. Red insulation is heat resistant, making it appropriate for high-temperature environments where the wires may be subjected to elevated temperatures. White insulation is a general-purpose insulation suitable for a wide range of applications where specific environmental factors are not a concern. Blue insulation is cold-resistant, making it suitable for low-temperature environments where the wires may be exposed to extreme cold. Green insulation is typically used for background conductors, indicating that the conductor is intended for grounding purposes and does not require insulation. It is crucial to emphasize that these color codes are generally accepted in North America and other regions that adhere to similar standards. However, it is always essential to consult local regulations and industry best practices for specific applications. The electrical codes and standards can vary from one jurisdiction to another, and it is the responsibility of the electrician or technician to ensure compliance with all applicable requirements. To ensure consistency and safety, it is recommended to verify the wiring color codes with local electrical codes and standards before commencing any electrical work. These codes and standards provide detailed information on the approved color schemes and wiring practices for different types of electrical systems. It is also important to document the wiring color codes used in each electrical panel or system to facilitate future maintenance and troubleshooting. Creating a wiring diagram or labeling each wire with its corresponding color code can significantly reduce the risk of errors and improve the efficiency of electrical work. In summary, understanding and adhering to electrical wiring color codes is essential for safety, efficiency, and compliance in industrial electrical systems. By following the standard color conventions for different voltage levels and conductor types, technicians can quickly and accurately identify the purpose of each wire, reducing the risk of electrical shock and ensuring the proper operation of equipment. Always consult local regulations and industry best practices to ensure compliance with all applicable requirements, and document the wiring color codes used in each electrical panel or system to facilitate future maintenance and troubleshooting. Remember that safety is paramount when working with electricity, and taking the time to understand and apply the correct wiring color codes can significantly improve the safety and reliability of industrial electrical systems. Understanding the nuances of industrial electrical wiring color codes extends beyond simply memorizing a table. It involves comprehending the rationale behind these standards, the potential consequences of deviations, and the best practices for implementation and maintenance. One of the primary reasons for establishing standardized color codes is to minimize the risk of electrical shock. Electricity poses a significant hazard, and accidental contact with a live conductor can result in serious injury or death. By adhering to a consistent color scheme, electricians and technicians can quickly identify the function of each wire, allowing them to safely isolate and energize circuits before performing any work. Another reason for using color codes is to improve the efficiency of troubleshooting and repairs. When an electrical system malfunctions, technicians need to quickly identify the source of the problem. By knowing the standard color codes, they can trace the wires from the point of failure back to the source, identifying any loose connections, damaged wires, or faulty components. This can significantly reduce the time required to diagnose and repair electrical issues, minimizing downtime and production losses. Color codes also play a critical role in ensuring the proper operation of electrical equipment. Many industrial machines and devices rely on specific voltage levels and phase configurations to function correctly. By using the appropriate color-coded wiring, electricians can ensure that the equipment is properly connected to the power supply, preventing damage to the equipment and ensuring optimal performance. The consequences of deviating from the standard color codes can be severe. If wires are misidentified or improperly connected, it can lead to electrical shock, equipment damage, and even fires. For example, if a neutral wire is mistakenly connected to a hot conductor, it can create a short circuit, causing a surge of current that can damage electrical components and ignite flammable materials. Similarly, if the phases in a three-phase system are improperly connected, it can cause motors to run backwards, damaging the equipment and potentially causing injuries. To ensure the effective implementation of color codes, it is important to follow certain best practices. Firstly, always use the correct color of wire for each application. Do not substitute one color for another, even if the wires are otherwise identical. Secondly, label each wire with its corresponding color code. This will help prevent confusion and ensure that the wires are properly identified in the future. Thirdly, create a wiring diagram for each electrical panel or system. This diagram should clearly show the color codes of all the wires and their connections. Fourthly, train all electricians and technicians on the standard color codes and best practices. This will ensure that everyone is aware of the importance of following the color codes and knows how to properly implement them. Fifthly, regularly inspect the wiring to ensure that the color codes are still visible and accurate. Over time, the color coding on wires can fade or become damaged, making it difficult to identify the wires. If the color coding is no longer clear, replace the wires with new ones that have the correct color coding. By following these best practices, you can ensure that color codes are effectively implemented and maintained, minimizing the risk of electrical hazards and ensuring the safe and efficient operation of industrial electrical systems.